Hi folks, welcome to the Art of Engineering, and this is episode 2 of How Works. In today's episode, we're going to look at how a transistor works, in this case, a bipolar junction transistor. Please stick around till after the little information slideshow, because I'm going to take you over to the test bench. We're going to set up a scope and a real circuit and have a play with the transistor to see exactly how it works and to get a little bit of an insight into a real situation. Let's go. The transistor, what it is and why it was invented. Now, these three gentlemen you see before you from Bell Labs in 1947 invented the transistor, and their names were John Bardeen, William Shockley, and Walter Brattain. Now, the prototype transistor was a point contact device, and it wasn't that reliable. But over time, William Shockley spent a great deal of time perfecting this prototype and came up with a 3-layer design that consisted of a base, collector, and emitter. Now, Bell Labs was getting these gentlemen to work on this project because they wanted a more reliable way of amplifying telephone signals so that they could do telephone calls over longer distances more reliably. Bell Labs, after all, was a telephone company. This device could amplify and/or switch electrical currents and replaced the thermionic valve. Now, the problem with thermionic valves, of course, is that they're not as reliable, they're very energy hungry, and also they are very large, much larger than transistors, obviously. But they are such a thing of beauty, and they glow warmly, and I would love to spend a little bit of time exploring this type of technology and maybe building some valve transmitters and receivers. Perhaps in the future this may happen. But without solid state electronics and the transistor, the world we know would not be the same. In fact, a lot of this information that I'm reading to you at this moment came from ChatGPT, a giant electronic brain that wouldn't have been possible without solid-state electronics. The space race and the Apollo missions to the moon would have been impossible without the transistor. This here is a navigation computer from the Apollo missions, and it has a whopping 74 kilobytes of memory. Anyway, folks, let's toddle off to the board and see how transistors actually work. The transistor. Now, transistors come in a lot of different packages, and you can see here, this is a 2N3053, which is the one we're going to be looking at when we do our test on the test bench. So stick around till after this, or fast forward if you want to get to the juicy bits. But we're going to make this transistor an amplifier and show you how it works with an oscilloscope and a signal generator. Another thing to understand about transistors is that you obviously just can't plug them in and off they go. You need to have a circuit around the actual transistor. That circuit is called a biasing circuit. And the biasing circuit just gets the transistor operating in the region where it's going to do what it needs to do, which is amplify or switch. So the values in that biasing circuit will be dependent upon what you actually want the transistor to do. Now, if you're worried about my credentials to be teaching all of this technical stuff, of course, I have to tell you, I'm a qualified radio officer, which means I basically know nothing. Now, as you can see, your transistor can be either NPN or PNP, and that's just how the 3 slivers of silicon are doped. If you haven't watched episode 1 on the diode, you might not know what doping is. Doping basically is something that you do to silicon or a semiconductor to change its conductive characteristics. Basically, pure silicon is a rubbish conductor. It's pretty much close to being an insulator. But when you add a contaminant, you can get it to behave a certain way. For instance, if you dope it with an N-type contaminant, you put a chemical in here that's an N-type, it'll produce lots and lots of electrons. We have our collector and our emitter.
we have our electrons that are free to conduct now because they've been doped N-type. We've got our collector up here with a positive voltage on it, our base with a smaller positive voltage, and our emitter with the negative voltage. Now, what they actually do is in the emitter here, they actually dope it so it's got more electrons than the actual collector. And you're going to find out why that is in just a second. Now, a p-type area is doped so it has positive charge carriers, and they are called holes. And I'm going to draw them on here. And there's a reason why I've drawn each of these NPN sections at different heights. It's because this section here, the emitter section, has more electrons because it's doped more heavily. And this is doped less heavily, but it's still got a lot of electrons in it. And that's the collector region. And in your p-type region, which is the base, you've got these holes. And I have drawn that area really, really thin because it is really, really thin. And there's a reason for that. And that is because you've got your base current, base to emitter current, and you've got your collector to emitter current. And you might notice here that this PN junction is forward biased. And if you've watched the first video, you'll know that if it has the correct voltage on it, which is about, for silicon, about 0.7 volts, that this will be conducting. So you'll have a small base current. And remember, all these arrows are conventional current, which is opposite to what electrons are doing. When we've got a positive voltage here, our electrons that are in the emitter, and there's lots of them, are going to jump into these little holes here and seek out that positive voltage. So the electron flow is going to be in that direction from emitter to base. But unfortunately, our collector base is reverse biased. So you shouldn't have any current flowing. And also, if you look at the collector emitter, you've essentially got a reverse bias condition. So you might be saying, well, how do we end up with a larger flow from the collector to emitter of current than from the base emitter if this is reverse bias? And this is where Shockley got very, very clever, Shockley and his team. He made this actual base region, or they made this base region, a lot thinner. And what that does is, when these electrons are sweeping up from the emitter, they fill these holes very, very, very quickly. And once they've filled these holes up, they're basically looking at a much larger positive voltage on the collector, and they go, hold on, we can't go this way, let's go this way. So what ends up happening is, you get a larger flow of current happening this way because the electrons are swept into that base region, fill up all the holes very, very quickly, and they go, we've got nowhere to go, let's keep going. Very, very quickly, I don't want to harp on about this, but just remember that these holes are exactly what the name implies. They're a hole in the silicon structure where an electron wants to be. So they don't actually move, they stay where they are. But because the electrons are moving or jumping through those holes, it's kind of like the holes are moving in the opposite direction to the electrons. Anyway, back to the video. And that is why the thing will operate as an amplifier. In a nutshell, what happens is, if you've got your small base emitter current happening here at the base, coming into the base, you will get a larger flow from collector to emitter. So if that's your flow there, we get our lovely amplified signal, if the whole thing is biased correctly. Hope that explains how this all works. I would strongly advise you to go look at video 1 about doping and diodes, because that will give you a better understanding of what I've just told you here. But if you understand this, that's great, because we're going to now go over to the test bench and have a look at how this works for real. Well, last night was a complete disaster. Stayed up till nearly midnight. Was trying to get a circuit built so I could demonstrate to you how that transistor works, and just put a small signal in using the arbitrary waveform generator on my brand new Hantek scope, and didn't isolate the signal from the actual voltages in the circuit. Should have used a capacitor. Really dumb thing to do. And I have blown up the AWG, the signal generator in the Crow. So very sad that I've destroyed a good piece of equipment. I've had a look online. I think there's only a digital analog converter chip and a operational amplifier on the board. Probably the operational amplifier has died, but it's service mount. So one day that will be a repair that I'll do on the channel. Me again. A new day brings new hope. I looked at a few teardown videos for this particular scope, and I will put a link below to that YouTube video that I watched because it's a great channel. He does lots of analysis of various pieces of test equipment, lots of teardowns. It's very useful. And he was nice enough to put an answer to the question that I put in the comment section. And he basically said what I thought would be the case, which is that it's most likely going to be the op amp that's on that board. So I have ordered the op amp and I'm going to have a go at replacing that op amp. So like all stuff ups, my stuff up becomes a video and hopefully we remediate the problem. Or you can watch me crying and throwing hundreds of dollars worth of test equipment across the room in utter disgust. But at any rate, the scope section, the digital storage oscilloscope section is still working. So like I said, if I have to buy a signal generator, I'll just buy a better signal generator with better specifications. But I am hoping to fix it because I think that's going to be a better option. It's going to cost me less money and I can spend my money in other places. But I did promise to show you a real test of a transistor to show you an input and output and how it amplifies and all that sort of stuff. So what I've done is I've gone across to J-Car, which most unfortunately is across the road from my school. I spent some money in there and I have bought myself a 555 timer to generate a square wave at an audio frequency and a BC547 transistor and a very, very simple biasing circuit. So I'm feeding the square wave from that 555 circuit, which is variable, into the BC547, and I'm monitoring the input at the base and the output at the collector. And it is in fact amplifying. So I will show you that circuit schematic. I will show you the actual breadboarded circuit, which is an utter and total piece of spaghetti. And I will show you what's happening on the scope. And then we'll leave it there. Let's go. So folks, this is the circuit that I'm using. We have a 555 here running on 5 to 15 volts with a 1 meg pot. You can find these circuits online all the time. They're not hard to find. And it's outputting a square wave at pin 3. And I'm feeding that into this circuit here, which is just a very, very simple single BC547 running a speaker with a single biasing resistor coming from the collector to the base. Understand that says 2K there. It's actually 2.2K. It also says 9 volts there, which I was going to run on 9 volts, but the 9 volt battery I had is just absolutely hopeless. The actual top of it's come off. It's so old. So it's in the bin. I'm running the whole thing off the 13.8 volt switch mode supply that's on the test bench, and hopefully we won't have any smoke coming out. And what will happen is I feed that square wave, which is an audio frequency, into this transistor. We will be measuring between the base of the transistor, which will be the input, and the collector over here, which will be the output. And hopefully we're going to see a big difference between the base and the collector, proving that our transistor is doing its job of amplifying this signal. Now please understand, transistors don't always amplify. Sometimes they do other things. Sometimes they're there to shift the phase or invert the waveform. They could be there as a buffer. There's so many reasons, but by and large, most often you're going to find that you want them to be amplifying signals. So we're going to show you that, hopefully, in the next piece of video. Fingers crossed. And here is our breadboarded circuit. Now, I know it looks like a bit of a mess, but we just need it to be a proof of concept. This adjusts the frequency. We've got our 555 IC hiding down there in this massive spaghetti, this bird's nest of wiring. And over here is our single transistor stage that I showed you on our circuit diagram, which is here. Okay, so as you can see, we have a 47 microfarad capacitor feeding that square wave from the 555 circuit into this single stage amplifier. And I've got the yellow probe number 1 on the base, sitting on the base here of the transistor, and on the collector, which is the output for this circuit, I have got probe number 2, the green probe.
And so we're going to jump over to the actual scope and have a look at how it all works. But let's just have a listen. I love all this stuff. Well, unsurprisingly, the circuit was designed for 9 volts, and I should have known better. But as you know, I'm rather flippant when it comes to electronics, and I'm constantly smoking components. So our BC547 has gone to the graveyard. I've put a 2N3053 here. I've put a series resistor in to lower the actual input. So if you look at the scope here, the input is set to 100 millivolts per division. So every time you cross one division here going vertically, it's 100 millivolts. This green is on 2 volts per division. So it's a way higher voltage per division. Watch what happens when we switch it on. As you can see there, these look like they're almost the same size. I'll just play with the frequency here. Let's go change it. Yeah, there we go there. But as you can see here, we'll try and get to trigger. As you can see here, that's nearly 2 divisions, but that's only 200 millivolts. This is 4 volts. So we're getting 200 millivolts turning into 4 volts. I don't even know how long this circuit's going to survive before it makes smoke. But all I do know is, as you can see there, that is a great demonstration of an amplifier. 100 millivolts coming in, or 200 millivolts coming in, and almost 4 volts peak to peak coming out. There you have it, folks. I've delivered on my promise, and it's time to say goodbye. Well, thank you for sticking around right to the end of the video. It's been a real adventure. I have created some more projects for myself, which is always good. And I was going to take out my brand new key here, J-style key here, and do some slow morse on the QRS net that happens here in Australia on the 80 meter band. I have a video on my channel on the hand playlist if you want to find out all about that. So for now, I'm going to say goodbye from episode 2 of how it works, and I will see you in the next episode. Got to think about what it's going to be about. 7-3.